All right, good morning, everyone. Can you all hear me? Thumbs up? Yes, okay. I had to change some of my computer setup here, so I wasn't sure if it was going to work. Okay, so we have kind of a layout here of what we're going to be doing today. We're going to do more exponential and log equations with some word problems in there. Thursday, we're going to finish up everything and start looking at the review for the exam, which is going to take place a week from today. So that's what we have in store for us. Are there any questions over anything? We have a full house. We have 22 people here, which is usually we're around 16. So welcome back, everybody. Make sure you have your calculators today. We're going to need these. So I wanted to just go and kind of talk about what we know how to do and what our goal is for today. So last class we determined how we can solve exponential equations. And an exponential equation is any equation where the x that we have appears in the exponent. So when you look at these two equations, we notice we've got x's up in the power, right? And then our base, the base is the e, okay? So we call that the base. And then of course, this up here is the exponent. And we know how to solve these using our calculator because we use this property, the property of e and natural log to solve those. So I'm not going to go through that. That's what your homework was over. But I would expect everybody in here could solve these two equations. Now, we also learned how to solve what are called logarithmic equations last time. And that is any equation where the x appears inside of a log. So here, notice we've got the x's are inside this log. And the log here that we're looking at, that is what we would refer to as the natural log. And again, we'd use our calculator to do that. So do I need to review either of these, or are we okay to move on? Is there any need to go over any of that? You're okay? All right, so now today, here's what we're going to try and do. We're going to try and solve more equations. Look at these first two. These first two are exponential, and these two are both log equations. And I want you to notice the main difference. On the first two, we have x up in the exponent, but do you see what our base is? See here, our x was up in the exponent, but our base was e, so we used our calculators to do that, right? Here, our base is no longer e, the base is 10, right? And then also on the log equations, we've got the x here, the x is in here, but notice that the log equation is no longer the ln, it's now log. And there's a difference between these two, all right? So that's what today is about. We're gonna figure out what does this mean and what happens when we have a 10 down here instead of an e. Okay, so we'll talk about that. And then after that, the ultimate goal would be to solve exponential equations and log equations where the base is any number, okay? Like it doesn't have to be e or 10. It could be anything. So here I'm going to highlight the exponential equation, the variables up in the exponent, but notice our base here is 7, right? And then with the log equation, we have x here, but this log now has a little 7 down there. So the question is like, you know, what the heck does log with the little 7 down there mean, right? So this is all stuff we're going to talk about today. Okay? So let's get into this. I'm going to remind you that the whole idea behind e and natural log was this. When we were looking at e and natural log, the idea was that if we started with some numbers and we sent it through the e function, it's going to spit out some numbers. And then our goal was to try and find a function that would take those numbers back to where they came from. And I told you, well, the natural log is the function that does that. And from that, we got two very important properties. The first property was that when you put natural log together with E, that they kill each other off and you get X. And that's the property we use to bring, like, to get the X out of the exponent. So that was a property here, very important. And then the other property is that when we took E and raised it to the natural log of X, this also, they kill each other off and you just get the X. So those are very important properties there. We have something very similar that happens when you look at, instead of E, we use the number 10. So if I were to start here with some numbers and send it through the function 10 to the X, then we would get some outputs, some numbers. And I can make a quick little table over here to show you. If you plug in X, here's 10 to the X. We could plug some numbers in here, 0, 1, 2, 3, whatever. 10 to the 0 would be 1, 10 to the first power would be 10, 10 squared is 100, 10 cubed is 1,000, right? So that's what would happen if we go from left to right here. Now, is there a function that takes everything back? And the answer is yes, and it's called the log function, not the natural log, the log function, log X. So on your calculators, you should have a key. You should have two keys. One of them is the ln. Remember, that's an L, not an I. Okay, the ln, we already used that key. But now I want you to look on your calculator for the log key. All right, make sure you have it, and let's just practice using it a couple of times. Let's just try, as an example, to take log of, let's say, 1,000. And when you do that on your calculator, does anyone want to tell me what they get? Or is anyone having trouble finding? You get 3. Yep. Okay, you should get 3. Now, this is why it's dangerous to be using your phone, because on the test, you can't use your phone. You need to make sure you're using a calculator, that you know where these keys are, because during the test, if you don't know where the keys are, there's nothing I'm going to be able to do for you. So you've got a week to get this figured out, right? So you get 3. How about this, log of 1? What do you get there?
Sir, can you scroll up real quick?
Yep.
Sorry.
No, it's okay. How far? Just
No, that's fine.
1? Okay.
Got 0.
So log of 1. Someone get something? I heard
0.
something. 0. Yeah. So think about it this way. If you look back up at the chart I made, 1,000, right? That 1,000, when we plugged into the log function, and went back to 3. And then when we plugged in 1, it got sent back to 0. Okay, so that log function is the inverse of the 10 to the X function. That means that we're going to have similar properties that we had like up here. One property that we're going to have is that log of 10 to the X should be X. And the other one is that 10 raised to the log X should be equal to X. So these are two new properties that we have that we want to be able to use. Okay? So make sure you have those written down.
I'm not sure if you saw in the chat, somebody asked if you could do one of each.
Oh, I didn't see that. Sorry, I've got, okay, so that's on the original problems we did from last time. I'm guessing, yes, one of these.
Yes.
Yeah, I don't mind doing one of those. Why don't I just do the harder ones? Okay. So I'll do them here because I don't want to copy those to a new page. Let's just do those here. I'm going to move fast though, because we did cover this already. So this one right here. When we do this, we have 4e raised to the 2x plus 1 minus 7 equals 324. So the whole goal right now, well, you have to recognize this is an exponential equation. So you have to recognize the x is up in the exponent. Once you realize that, your goal is to try and get this e to the 2x plus 1 by itself. So the first thing that I would do here is I would add 7 to both sides, and that would get rid of the 7 over there. So I would have 4e to the 2x plus 1 equals, now when I add 7 over there, I get 331. And then I almost have the e part by itself. I need to get rid of the 4. And since that's multiplication, I'm going to divide both sides by 4. And so now I'm going to go on my calculator and I'm going to figure out what 331 divided by 4 is. I get 82.75. Okay, does someone want to tell me what the very important next step is?
You put the ln?
Mhm. ln on both sides. So you're going to bring natural log of the left side and then natural log of the right side. Whatever you do to the left, you have to do to the right. So the whole point of that is the fact that the natural log and the e kill each other off. That was that property that I just explained on the second page right here, these properties. When you put natural log and e together, they go away and you just get whatever was up top. So what we're going to get is this 2x plus 1. That's all that's going to be left on the left-hand side. And then on our calculators, we have to figure out what natural log of 82.7 is, or 75. And I get 4.15. I'll just say 4.15 or 4.415. And if you round, that's okay. And now at this point, what you're looking at is just a linear equation. This is back to stuff we've done before. We're just going to try and solve. We're just going to try and solve for that x. So I'll subtract 1. We get 2x equals 3.415. I need to get rid of the 2, so I divide 2, and I get x is equal to 3.415 divided by 2 is going to be 1.707. There we go. Okay. So with this problem, it's all about isolating the thing with the e, get it all by itself, then bring in the property, the natural log on both sides, and then you'll have a linear equation that you just go solve. Now, on this equation, okay, that's a log equation. I'll do the harder of the two there. It's the same thing, except that the thing you're trying to get by itself is the log part. We're going to try and get that by itself. So we subtract 7 on both sides first. Okay, that'll give us 3 natural log of 2x plus 1 equals 95. Take away 7 is 88. Next step, divide by 3 on both sides. To get rid of that 3 there, you'll have natural log of 2x plus 1 equals 88 divided by 3. You'll get a repeating decimal here, so I'm just going to put 29.33. And now the very important step, we've got the natural log isolated. We want to kill the natural log off, so we have to come in with the e. Now this is a little different. You're not doing e right next to it. You're going to write e on both sides, and then what you're doing is you're taking whatever's on the left, that becomes the power on e, and then whatever's on the right becomes the power on e. So what you're really doing is you're raising e. You're taking e and you're raising it to both sides of the equation. So e gets raised to the left side, and that must be equal to e raised to the right side. The whole point of that is that this e and natural log kill each other off. Again, that's the property that I explained here. E and natural log, they kill each other off. And so I'm just going to get the 2x plus 1 here. And then here, uh-oh, shit, that's going to be a huge number. E to the 29, uh-oh, that may be too big. E to the 29.33. I just realized that's a huge, oh my gosh, that's a huge number. Okay, well, I made up this problem on the fly, so This number is just ridiculously big. I would not do that to you on the test. Let's just to make this easy, let's just say that this side came out to be like 5, 4, 6, 8, 3, 6, 0, 7. That's not what it is, but let's just say that's what it is. Now, this is a linear equation. Subtract 1 on both sides. Once you do that, you divide by 2. Does that make sense? I'm not going to finish that off. Once you're to the linear equation, you should be able to solve that. Now, the good news is we're going to be doing pretty much the same thing with this new idea, okay? With these two new properties. We're just going to be using a different key on our calculator. All right, that's going to be the difference. So let's do these problems that I said we would look at today. These right here. Let me see if I can grab these. All right. Okay, so let's do A. So A is what type of equation? What type of equation is this? I already said it, right? It's exponential, but that's the thing you want to be looking at. You know, is the x up in the exponent? Yes, right? Now, once you know that the x is in the exponent, you know it's an exponential equation. The next thing you need to look at is what is the base? And the base is 10. So since the base is 10, we need to undo that, right? And to undo that, we have to use the inverse of 10 to the x, which is the log key. So at this point, I'm going to take log on both sides of the equation, not natural log, log. And the whole idea there is that the log and the 10, those are going to cancel out. I'm just going to get the x on the left. And on the right-hand side, I need to actually use my calculator to figure out what log of 25 is. So I'll let you do that while I see if I can't find my, Someone have it?
1.397.
1.397? Yep, that's what I got. 1.397. Close enough. Again, we might all be off a little bit with our rounding, okay? All right, now let's look at B, because B is a little different, right? B has a lot more crap in there and it looks confusing. 4 times 10 raised to the 2x plus 1 minus 7 equals 324. If you look at this right here is exactly the problem that we did right here. Okay, it's this problem. Do y'all see that? It's the same exact thing, except instead of E, I have a 10 there. Do y'all see that? This right here is exactly this problem, but with a 10 instead of an E. So because of that, I still want to try and isolate this by itself. I need to get that by itself. Now, a big mistake students make is that they'll do 4 times 10 and turn that into 40. Okay, students will go like this. They'll go, oh, that's just 40 raised to the 2x plus 1. That is incorrect. And it's incorrect because order of operations always tells you have to do exponents first. So you'd first have to do 10 raised to this power. You don't know what that power is, so you can't actually do that operation. Multiplication would come after that. So you are not allowed to do this. Is that clear? So we just need to isolate the green. So we'll do the same thing we did a minute ago. We'll add 7 to both sides. Okay, that'll give us 331 on this side. We'll have 4 times 10 raised to the 2x plus 1. Anyone have an idea what to do now? Should I call on people today?
Would you divide by 4?
Divide by 4. Yeah, let's just get rid of that 4. Let's just divide the 4 out. Okay, just like we did earlier. And then we'll have 10 raised to the 2x plus 1 equals, we did that earlier. What was that? 82.75. Okay, and now the very, very important part. Let's see, I'll pick up from where I was last class. Is Sammy around today? Sammy, no, Sammy.
Oh, can
Sammy?
you hear me?
Yep, I can hear you. And I'm sorry, if you've already responded, it's hard for me to tell who's saying what, so I'm just gonna call on people. Sammy, what do we do now?
You're going to try and get rid of the 10,
Okay, so how do I do that?
the log.
Okay, good, right? The LOG button, right, on the calculator. So log 10 to the 2x plus 1 equals, we have to do it on the other side, log 82.75. And remember, on the left-hand side, you're not actually doing log on your calculator. These two just go away. They're just gone, okay? That's the whole idea. And that leaves you with the 2x plus 1. And then, Sammy, do you have a calculator that does log? Yes?
No, I don't have a calculator right now.
You don't? Okay, so somebody that has a calculator that'll do log, want to tell me what log of 82.75 is? I think we did it already, didn't we? Yeah, didn't we? It was, oh wait, no, that was natural log. See, so we can't use this, you see? Because we did the natural log of 82.75. We're not doing natural log, we're doing the log. So anybody have it?
I got 1.92.
1.92? Okay, I'll confirm that. Yep, that's what I got. 1.92. There we go. And now again, you have a linear equation. We're just going to solve for x. So we subtract 1, subtract 1. That gives us 2x equals 0.92. And then we divide by 2, right? Divide both sides by 2. So you should get, I think, 0.46. There we go. Now, like big picture, like what did we just do? Like what was all this? What did we do? We solved this equation, right? We took this equation and we solved for x. That means that if we were to go and replace that x with 0.46, this should be true. In other words, if we do 4 times 10 raised to the 2 times 0.46 plus 1, take away 7, we should get 324. I'm not going to do it, but you would do 2 times 0.46. That would give you 0.92 plus 1 would give you 1.92. So you got 10 raised to the 1.92 minus 7. So if you did this on your calculator, 10 raised to the 1.92, then multiply it times 4, and then subtract 7, you should get 324. Okay, or close to it. There, it'll be off because we rounded, but so we've solved the equation. Any questions here? Okay. All right, so let's see. How do we do C then? Let's see. Now C is different, right? C is now a log equation. Let me do this on a new page. So C is a log equation. Log x equals 4. So to do this, what we're going to do is try and kill off the log, right? We have a log, the x is inside the log. We want to kill it. So we killed the natural log by bringing in e on both sides, right? That's what we did. Here, we have to understand that the inverse of log is 10 to the x. So what I'm going to do is I'm going to put a 10, and then I'm going to raise both sides of the equation to the left and right hand sides respectively. So I'm going to go log raised to the left side, 10 raised to the left side equals 10 raised to the right side. Now by design, the 10 and the log will kill each other off. You get x. On the right side, 10 to the 4th is 10,000. So your answer is 10,000. Any questions?
Why did you do?
What?
Go ahead.
Why did you do to 10?
Why did I use the 10?
Yes.
because we were just, when I started this out, I said, look, when we talk about the exponential function, the function that undoes it is the natural log function, right? But that was what we learned last time. Today's new thing is if we have 10 to the x, the inverse is the log. So if you put log together with 10 to the x, you get x. Or if you do 10 raised to the log of x, you get x. That's why I put the 10 there, because I'm dealing with log, L-O-G. And so anytime you deal with L-O-G, you're always going to use 10. Is that all right? Now let's look at D. I need to change D because the numbers are going to get too big. So if you don't mind, let me modify this. I'm going to change the equation a little bit. Let's just make our numbers work out better. Let's do this. 3, 4, 4. Let's go 4, 12, 12. Let's make that equal 20. No. Let's make that equal 9. Okay, instead of 95, make it 9. Oh, I forgot the +7. Oops, I'm sorry. +7 equals 9. Okay, so we're redoing that, but we're changing the 95, okay, to 9. All right, so we look at this, we realize we have a log equation, the x is inside the log there. We need to get this in green by itself. First, we subtract 7 on both sides. That gives us 2. Next step, get rid of the 3. To get rid of the 3, we divide both sides by 3. log of 2x plus 1 equals 2/3, which is 0.66 repeated. Any questions on this? Subtract 7, divide by 3. We've got the log by itself. Now we want to undo the log, right? We want to undo it. This is what Jesus was asking. Why do we come in with the 10, right? Well, we come in with the 10 because we have a log, L-O-G. So I'm going to do 10. And I'm going to raise both sides to the left and right-hand side of the previous equation, respectively. The whole idea there, again, is that this 10 and this log will kill each other off because they're inverses. And then on the right, I need to get on my calculator and I need to do 10 raised to the 0.666. That should give you 4.63, something like that. Again, raising 10 to the 0.66 is something you need to be able to do on your calculator. So make sure you can do that. And then the rest is just linear equations. Subtract 1, subtract 1. You get 2x equals 3.63. And 3.63 divided by 2 is 1.815. There we go. We've solved for x. Any questions?
Hey, sir,
Yes.
I got 1.817.
That's okay. That's okay. That just means that there was some different rounding probably when you did it on your calculator. That would be okay on a test. You just need to make sure that on the test you're showing me the steps, and I'll be able to see where the round. I bet you anything was like right here when you did this. You probably got something a little different right there. But you're okay with that. Don't worry.
Okay, thank you.
Okay, so our last thing that we want to be able to do is solve these types of equations right here. So let's take those over and let's take a look at them. And let's see why we're going to run into a pretty significant problem. All right. So let's take a look at this first one. A. 7 to the x equals 25. So the question here is, what power do you raise 7 to in order to get 25? So think about that. You know, what's 7 to the first power? Well, 7 to the first should just be itself, right? 7. What's 7 squared? 7 times 7, right? Isn't that 49? We're saying, what power do you raise 7 to in order to get 25? So is it reasonable that our answer should be somewhere between 1 and 2? Because 2 gives you a number bigger than 25 and 1 gives you a number smaller than 25. Our answer should be between 1 and 2, but what is it, right? So to do this, we would like to get this x out of the exponent, right? We'd like to get it out of there. So we'd like to kill off the 7. So the question becomes, what do we use to kill off the 7, right? If you go back and look at, let me see, this, we know that if we have e as the base, to kill off the e, we use the natural log. If we have 10 as the base, we use the log key to kill off the 10, don't we? But now we have 7. How do we kill off the 7, right? Does this make sense? Now, you might think, oh, there's a key for that, right? Well, the problem is, what if I used a different number, like 8 here, or 9, or 11, or 17, or 21, or right? You don't have enough keys. You couldn't possibly ever have enough keys to do this. Does that make sense? So there's got to be something different, and there is. Okay, I just want everyone to understand, appreciate that right now we don't have any way of doing this unless we can somehow figure out what the inverse function is that takes you back, right? If I could figure out what that is, that undoes this, then we'd be in business, right? Agreed? So here's where we have to just take a pause and we have to understand a little bit more about these inverses, all right? So first thing, let me just, I have to do this best, I think I have to recap where we are. So if we have e to the x, right? If we have e to the x, then the natural log of x is the inverse. All right. So we know that e and natural log, they kill each other off. If we have 10 to the x, then the log function, log x, is the inverse. And when we put those two together, they kill each other off. But what if we have a to the x? So now this is what I'm getting at is this is a very general statement I'm making. Instead of actually giving you the number, I'm just saying, look, what if it's a? What if it's 7? Or what if it's 4? Or what if it's any number? What's the inverse? Well, then the way we write this is log base a of x is the inverse. Okay, so this is new. This is brand new. I'm telling you this, okay? Log base a of x is the inverse. So for example, if we have 7 to the x, then log base 7 of x is the inverse. Another one, if we have 4 to the x, then log base 4 of x is the inverse. If we have, I don't know, we could put anything we want here. If we have 12 to the x, then log base 12 of x is the inverse. So now we have this new little like subscripting here. And what that tells us is what the base was over here. Now, immediately you should be asking yourself, well, if these are the inverses, where the hell's that key on my calculator, right? Like, where's that log base 7 key so that I can use it? Back here, we're like, okay, how do we solve this here? Right? How do we solve this equation? It makes sense that if we know that the inverse of this is log base 7, then we should just do log base 7 of 7 to the x on the left and log base 7 of 25 on the right. Does that make sense? That, you know, if this is true, if this function is the inverse of 7 to the x, then we should just do this on both sides. These two will kill each other off, we'll have x. And then what we need to be able to do on our calculator is that. So that's when you're like, well, where's my log base 7 key, right? It's not here, okay? It's not here. It's not. Now I'm going to show you, there's a way we're going to get around it, but I just want you to understand where we are and where we're stuck, okay? So I'm going to leave this as an open question. How are we going to solve that? Don't know yet. Let me give you a different example. I'm not going to say B here. Let me just give you this one. What if we have 4 to the x equals 21? Well, the base is 4, so the inverse of that should be log base 4. So what I would do is I would take log base 4 of 4 to the x on the left and log base 4 of 21 on the right. They kill each other off on the left. I get x is equal to log base 4 of 21, but I have no idea how to do that because I don't have that log base 4 key on my calculator. So again, we're stuck. Yes? Okay, well, I have good news. All right, I have very good news. Well, I don't know if it's good news. It's news, all right? In order to get around all of this, we have a very important formula. It's called the change of base formula. Very, very important formula. Here's what it says. Change of base formula says this. If you have log, and if your base is a of x, if you have that expression right there, this will always be equal to the natural log of x divided by the natural log of a. Okay, that is something you will definitely need for the next test. Okay, so let's see what this is saying. Let me try and give you this with these examples up here. I'm going to bring these two down here. Where were we? We were stuck at this point, log base 7 of 25. We were stuck there, and we were also stuck on the other one, which was log base 4 of 21. Right? Those were the problems we were stuck on just a minute ago. But if we look at this formula, the x is this number, right? Well, let me do them one at a time. And then the a is that number. So in order to figure out what this is, using that formula, this should just be the natural log of something over natural log of something. What number goes where? What number goes on top? The 7 or the 25?
25.
25 goes top and 7 on the bottom. Now, do you have a natural log key on your calculator? Yes, right? And so I'm just going to do this on my calculator. Natural log of 25 divided by natural log of 7. Please make sure you do this on your calculator before the test, okay? Because people will type this in incorrectly. The correct answer to that is 1.654. If you're not getting that, then that means you're doing something wrong when you're typing it in. The other one would become natural log of 21 over natural log of 4. And so I do that on my calculator. And my answer there is 2.196. Okay, so I'll offer 2 points bonus right now on the next test. If somebody can explain to me just in words why this formula is so important to us. in terms of our ability to calculate logs. What does it mean in terms of our calculator? What does it mean? Go for it.
It gives us an actual formula to input into our calculator
Okay.
where we wouldn't have one otherwise.
Okay. So let me try and get you to expand on that. How many keys does my calculator really need then? How many log keys does my calculator need?
1.
Just one, right? That's it. That's why most calculators only have, well, all of the calculator that's like required for this class has the natural log key and the LOG key, has both of them, right? Has both. But more advanced calculators, like the one I'm using here, only has a natural log key. And the reason is because most people that use this calculator know this formula and realize that you only need a natural log key. That's all you ever need. In fact, you don't even need the LOG key. And let me show you why. When we write log, okay, when we write that, we know that's the one that goes with 10, right? That's the one that goes with 10. In reality, this is log base 10. That's what it really is. And so if I needed to do log of, let's say, 30, I could just use my calculator. But if I use the change of base formula, I'd understand that that's a 10 down there. And I would just do natural log of 30 over natural log of 10. And see, I only need my natural log key to do that. So it's understood that there's a 10 down there, even though there's not. Okay, I'm not going to get too far into that, but this is good news because now we should be able to solve any exponential equation at all, okay? Any of them. So good news. Let's do those examples that I hadn't done here. All right, so we did the first one, right? We got the answer there. We're done. Let's do part B. So for part B, we have 4 times 7 to the 2x plus 1 minus 7 equals 324. Okay, we've been through this a couple of times now. We've had an E here for the 7. We've had a 10 there, and now we have a 7. So our goal is to isolate this. Do not multiply 4 times 7. Again, you cannot do that. Don't turn that into a 28. You have to get the thing in green by itself. So add 8 to both sides. Or sorry, add 7. I don't know why I said add 8. Add 7 to both sides. All right, once we add 7, we divide by 4. So we'll have 7 raised to the 2x plus 1 equals, okay, now we've done that a couple of times, but I forgot what it was. Was it 82.75?
Yes, sir.
Okay, 82.75. And now we have the 7 to the thing isolated. We need to kill the 7. So how do we kill the 7? Log base 7, right? Log base 7 like that. And then 7 to the 2x plus 1. Whatever we do to that side, we must do to the other side. The whole idea of the left side is that they will kill each other off. I'll have 2x plus 1. On the right side, okay, so now we have something new. How are we going to handle the right side? Let me see. Is Patrick around?
Yes, sir.
Are you following along, Patrick?
Yes, sir.
Okay, so how would I do the right side of this equation?
Would we just plug it into the calculator?
Yeah, so how though? Like tell me what I'm plugging in. Oh, sorry, forgot to silence my phone. So how does that go into the calculator? Because we don't have a log base 7 key. right?
No, sir.
Okay, so what do we use?
So the way I've been using it on my calculator, I can input it like that manually, and it gives me.
Okay, so some calculators do allow you to put the base in. Some do. But if you don't have that ability, you would have to go back to this thing, right? This is your change of base formula. We have log base 7 of 82.75. So we've got to plug that in here. So the right side is actually going to become natural log of 82.75 over natural log of 7. And you got to figure out what that is. All right. So I'm going to do that right now. Are there any questions on that while I'm doing this? It's an extra step that we have to do, right? I mean, this is a little more tedious than the previous ones, but it can be done.
Sir, I have a question.
Yes.
So what determines if we use log or natural log or any of those?
What determines it?
Yeah.
The base. So this 7 is what determines whether or not I'm going to be using, let me go back to this original thing here. So when we're solving equations like this, if we see E here, we're going to be using the natural log. If we see a 10, we're going to be using the LOG button. If we see something other than those two, any other number other than E or 10, we have to use this change of base formula. Does that make sense or no?
Oh, okay, yeah. Thank you.
Okay, no problem. So I'm going to subtract 1 on both sides now. 2x equals 1.269. And 1.269 divided by 2 is 0.6345. All right. Let's move on to part C here. Part C, we're looking at this one right here, is log base 7 of x equals 4. So now we have a log equation because the x is inside the log. It's not up in the exponent anymore. So we want to try and kill the log off. So how do we kill the log off? Any ideas here?
Is it the one with the 10? Like 10 to the x?
Yes. Yeah, so when we go back and we look at how we did this, right? When we were looking at this log equation, when we were trying to kill off the log, we used 10, right? And that's because it was log, L-O-G. But now we're trying to kill off log base 7, right? So instead of doing a 10 on the bottom, I'm going to go 7 on the bottom and then raise 7 to both sides. Do y'all see how I'm putting 7 here because it was a base 7 log. And that means that these are going to kill each other off and leave me with the x. And then the right side, I just get on my calculator and do 7 to the 4th power, which is 2,401. Maybe I should just do another one because those are pretty, once you understand them, they're pretty straightforward. What if we had this log base 3 of x equals 200? No, too big, sorry. Let's make that 4. Okay. How about that? So how do we kill off the log base 3? What number do we use on both sides?
3.
3. Okay, so I'm gonna go 3, and I'm gonna raise the left-hand side to log base 3 of x and raise the right-hand side to the 4th. The 3 and the log are gone. You have x equals 3 to the 4th, which should be 81. Is it Tuesday? Yeah, it's Tuesday, right? Every Tuesday, the college sends out these emails And it's like 20 of them in a row that all come at the same time. So my phone's sitting there blowing up. Okay. Now, I think I'm ready to move on. Are y'all okay with this? I mean, you're going to get some practice with your homework, all right? But I think we need to move on to the next concept, all right? Because we only have about 25 minutes left. So in theory now, we should be able to solve any log equation. We should be able to, or any exponential, any log equation, we should be able to solve it because we have the natural log key on our calculator. We should be able to do anything. So now we're going to do applications, right? So we're going to do some applications.
I'm sorry, can you explain one more time, like how we know when we need to use log?
When you need to use it?
Yeah, like, cause like these equations are like similar to the ones we did last week, so I'm kind of lost.
Well, last week, every equation that we dealt with last week involved E, didn't it, as of the base?
Yeah.
And so when you look back on last week, everything I ever did, we came in with the natural log because the natural log kills off E. What today is about is that if your base is something other than natural log, like if your base is 10, or in this case 7, then that's going to dictate what log you use. So yeah, if where did I write that down? So if you have an E in the equation, E to the X somewhere in there, you're going to be using the natural log on your calculator. If you have 10 to the X, then you're just going to be using the regular log key. And if you have A to the X, then the inverse is this, and you're going to be using the change of base formula. You're going to be using the log base A of X equals natural log X over natural log A. I mean, that'll be something you have to do somewhere within the problem. Does that help or no?
Yes.
Okay.
Thank you.
Yep. Okay, so applications. One thing we've already done, okay? We've already done this. Remember this formula, the shampoo formula? Right? I'm going to put a check mark next to this because we've already done this. I gave you problems last time where what we were trying to figure out was either the interest rate or the amount of time that we needed to leave money in a bank, right? We did several of these examples last class. And when we did them, I'll go back to them like this, right? We were solving here, you can see we were solving for the interest rate. We were solving for that R. The R is up in the exponent. But notice that in these problems, the base was E, right? And that's why we came in and we used natural log on both sides. So we've already done that. We've already used logs, and specifically the natural log, to solve things like that. We're going to look at a couple more applications. The first one I want to do is related to this, but it's not money. It doesn't have anything to do with money. Okay, so this has to do with what we call exponential growth models. So let me just write it down first. Exponential growth or decay models. All right. So I'm gonna write a formula down here, okay? And when I write this formula down, just write it down, and then we will talk about what it all means after I do it, okay? So I'm gonna put here P equals P sub 0 e to the k times t. All right, so once you write this down, I want you to first realize that this formula is basically the shampoo formula. It's the same thing, we're just using different letters. Instead of A, I have P. Instead of P, I have P subscripted with a 0. We have E, right? E is the same. And then instead of R, we have K, and then we still have T. Do y'all see that this is basically the same shampoo formula? Okay, So let me explain what this is, how this formula is different, because it doesn't have anything to do with money, all right? P sub 0 is the initial amount. Now, that's all I'm going to say. It's the initial amount. That can be anything. It doesn't have to be money. Now, in the shampoo formula, P was the money we put in the beginning, right? That's how much money we started with. So here we're just saying, hey, it's the initial amount or the starting amount, no matter what it is. Could be money, could be number of people, it could be the number of bacteria, the number of viruses, whatever it is. That's just the starting amount, all right? T is time, okay? P, the left-hand side of the equation, is the amount at time T. So the left-hand side of the equation tells you how much of whatever it is you're looking at, population, bacteria, whatever it is, it tells you how much is there at a specific point in time. And then K, the very important number here, is what we call the growth or the decay constant. Now, in our shampoo formula, the R was this number here was the interest rate, wasn't it? It was the interest rate, but for this, K is just some growth or decay constant. That's what we call it. So this formula is used anytime you want to look at something that's growing over time exponentially or decaying over time exponentially. So let me show you how this is done, okay? Let me show you how we actually use this formula. I'm trying to determine how I want to do this. All right. Yeah, let's do it this way. Okay, does anybody in here know what this is? Half-life. And I'm not talking about the video game. Does anyone know what the half-life of something is? If you do, feel free to speak up. If not, I can explain it. No? Okay, so certain substances on Earth, okay, have this thing called a half-life. So one very common, let's just look at one thing in particular. There's a lot of things that you can talk about their half-lives, but let's look at one thing in particular, right? And it's something called carbon-14. Does anyone know what carbon-14 is? So your body, every living thing on the planet, okay, every living thing produces carbon-14. Okay, so your body right now is producing carbon-14, and all humans maintain a certain level of carbon-14. Now, as soon as you die, or as soon as whatever it is that's living dies, your body is no longer able to produce the carbon-14. So the carbon-14 starts to go away over time, it starts to decay. And the way that it works is that, let's say, think of it like a campfire, okay? You know, if you have a raging campfire, here, let me do it in red. That way it's, let's say you have a campfire, right? You're gonna do s'mores, you're all sitting around, here's your raging fire, it's really, really hot, right? Now, if you let it go over time, it's going to start to die down, right? So maybe in 2 hours, the fire is gonna be less, right? And then maybe, so that's 2 hours. And maybe 2 hours later, it's going to be even less. And then 2 hours later, it's going to be even less. And then 2 hours later, it's going to be less. But you come back the next day, right? You go to sleep in your tent, you come back the next morning, you're making breakfast, right? And you go and you realize, shit, it's still hot. Like there's still like little coals in there that are burning, right? So it's like a fire that it keeps decaying away, but it kind of never really goes away. Now, we know the campfire eventually does die, but when you talk about things like carbon-14, a half-life is the amount of time it takes for half of it to go away. Okay, so the best illustration I can give you is a piece of paper. If I take a piece of paper, let's say this is all the carbon-14 that's in your body. After a certain amount of time, half of it will be gone. Okay, it takes a certain amount of time for that to happen. And then that same amount of time goes by and half of that goes away. Okay, let me look it up real quick. I'm just going to go to Google real quick, and I'm going to put in half-life carbon-14. The half-life, 5,730 years. 5,730 years. Okay, that's the half-life of carbon-14. So let me start this over. You die, okay? You've got all your carbon-14 in your body, you die. Okay, it starts to go away. 5,730 years from now, half of it will be gone, all right? Then in another 5,730 years, half of that's gone. And then in another 5,730 years, half of that's gone. And then another 5,730 years, half of that's gone, 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 half of that's gone. See what I'm saying? Like, it's still here though, right? There's still some. There's still some. And I can keep doing half of that and then half of that. So what scientists do is when they go and they find a bone, right, sitting there, they dig up a bone, they measure the amount of carbon-14. And if they know how much carbon-14 is there, they can actually go backwards and figure out how old this thing is. Like, when did it live? And when was this thing living? Okay. And this is what they use. This is the formula they use to do that. So I'm going to show you exactly how they do it with carbon-14. All right. Does this all kind of make sense? What I'm getting at? I mean, you kind of have a basic idea of the half-life. The half-life of something is the amount of time it takes for half of it to go away. Okay, that's what a half-life is. So I want us to take this formula and I want us to think about something. Let's say that at the beginning, we have a bone, right? We find a bone and we measure it, or I'm sorry, forget the bone. Let's not do the bone. Let's look at this formula, and I want you to consider this. Okay, so just write that down and let me explain why I wrote this down. I know I'm given, okay, so I have to know this information. I have to know the half-life of carbon-14, which is given to me to be 5,730 years. If I know that, then what I can say is that if time, right, if time is 5,730 years, then that's how long it will take for half of it to go away, right? So if I start off with this much, right, that's the starting amount. The ending amount, I want it to be half of that, half of the, so if I end here with half of what I started, it should take 5,730 years. Now, when you look at this equation, does anyone have any questions on why I wrote this down? Does everyone understand why the half is there? I'm trying to figure out, if I start with however much it is, it should take this much time to become, turn into half of it. Any questions? I'll do another example after we get through this, but okay, so if I have this equation, everyone, I want us to try and solve this. I would like for us to solve this for K. Because if I can figure out what K is what we call the growth or decay constant. This will give us the decay constant for carbon-14. So to do that, I'm going to try and isolate the E. This whole thing I'm going to try and isolate. And so the first thing I should do is probably divide both sides by this amount. And when I do that, it's going to go away on both sides, which is really good. That leaves us with a half equals E. Now watch, I'm going to write that as 5,730 times K. So I just switched the order of those. So do we have the E isolated? Is it by itself? Okay, so how can we kill the E? Both sides with what?
Ellen.
ln. Okay, so I do ln. I'm going to change 1/2 to 0.5. Then ln of e to the 5730k. On the left-hand side, I have to do that on my calculator. Natural log of 0.5. I get negative 0.693 equals, and then on the right-hand side, the natural log and e kill each other off. Get 5730 times k. And now what I'll do is I will divide both sides by 5730. Oops. I'm going to get a very small number. Watch, I'm going to get negative 0.000. I'm going to go out as far as my calculator goes. 1209424. That's what K is. Okay, so recapping what I've done so far. Somebody told me that the half-life of carbon-14 was 5,730 years. I used the original formula, plugged in 5730 here, did a half of the original amount. These things canceled, did natural log both sides, and I figured out what K is. Now, why is that so important? Here's why. This original equation right here, I know for carbon-14, okay, so for carbon-14 only, for carbon-14, we have this formula, P equals P sub 0, or P naught, e to the negative 0.001209424 times T. That is what we call the growth model for carbon-14, or actually it's a decay model, because it's getting smaller and smaller over time. We're going to have to do another example of this. I understand that, okay? But let's just stick with this right now. Any questions on how we got K? Somebody asked in the chat if this is what they use to do carbon-14 dating, and yes, this is exactly how they do it. So all the scientists, they have this is the formula that they use. So now let's see how they do it, all right? This formula is now ready for us to actually apply to the problem. So let's do this. A bone is found and the carbon-14 is measured. Scientists determine the bone contains 0.02% of its original carbon-14. How old is the bone? I have 5 minutes to finish this. I need this here, and then I also need this. All right. Okay, y'all ready to do this? You ready? All right. I'm going to use this formula. And I'm trying to figure out how old the bone is. So I need to solve for t. Hey, guess what? T is up in the exponent. That means this is an exponential equation, right? We can solve for variables up in the exponent because we've learned how to use logs and stuff. But I need to fill out the rest of the formula. So remember what p sub 0 is, right? P sub 0 is the amount that we started with, right? The amount of whatever it is. We're talking about carbon 14. So how much did this bone start with? Well, when it was alive, it had 100%, right? It had 100% of its carbon 14. So I'm going to replace that with 100, which represents the 100% that it had when it was alive, right? That's the original amount of carbon 14 that was there. So I'm going to just put 100 there. I'm not going to put a percent. E to the negative 0.0001209424 T. Now, P is the amount after a certain amount of time. Does anyone have an idea what that would be? P0 is what the carbon that we started with. P should be what? P is the amount after a certain amount of time, right? After some certain amount of time. So shouldn't that be the amount of carbon 14 that was there when we found the bone? Right? That's a certain amount of time has gone by since it died. And so this should be the 0.02. And we're going to leave it as 0.02 because the 100 represents the percent and 0.02 represents the percent that we have here. Now, we only have 2 minutes. Can you solve this equation? You want to get this by itself, right? So what would the first step be? Do you want this by itself? Get rid of the 100, right? Divide both sides by 100. And when you do that, you should get 0.0002. Now what?
ln on both sides.
ln both sides. Hold on, I messed up. So ln on both sides, and we're using natural log because we're trying to kill off e, right? That's the whole reason I'm bringing natural log in, because the natural log and the e are going to kill one another off. They will kill each other off. On the left-hand side, I got to get on my calculator and do this. I get negative 8.5172 equals, now on the right side, everything goes away except all that stuff that was up top. See, we're just using uglier numbers, but it's still the same procedure. Last step, what's the last step? You want to get t by itself. Divide both sides by negative 0.0001209424. Both sides. Negative 0.0001209424. So I'm gonna do that on my calculator. I get 7423.55 equals t. So how old's the bone? About 70,000 years or so. That's how old the bone is. So 70,423 years old. Now, look, I'll tell you that it's not a perfect science. In other words, I mean, what a scientist would probably say is, you know, it's about 60 to 80,000 years old. Like this is going to give you a ballpark. It's not going to nail it down like to the exact hour. It's just a general to give you an idea of like what period of time it came from, but it's not perfect. Okay, we're out of time. So look, what you need to do for homework, you know what, let me do this because we're out of time. I'm going to email everybody the homework assignment, like what you should look at, okay, because we're almost out of time. And make sure you're here next class because we will finish up more application and then we'll talk about the exam. I'll be sending out a review for you to go through for the weekend. Everyone have a good day.
Thank you, sir.
Thank you.
You.
Thank you, sir.
You're welcome. Have a good day.